As children, we learn to navigate the world through a very simple set of rules: up, down, left, right, forward, and backward. We map our lives onto three rigid dimensions of space, and we watch events unfold to the steady, unchanging rhythm of a universal clock. But there is a glaring problem with this intuitive picture. You can walk left, and then you can turn around and walk right. Space lets you move freely. Time, however, drags you by the collar in exactly one direction. You can drop a coffee cup and watch it shatter, but you will never see the porcelain shards leap off the floor and rebuild themselves. This one-way street is driven by entropy, the mathematical rule that states physical systems will naturally degrade from concentrated order into disordered, chaotic waste heat. In 1862, the 19th century physicist Lord Kelvin carried this logic to its grim conclusion. If the universe is a finite machine burning usable energy, it must eventually wind down into a dark, frozen state of universal rest and death. Because time forces the cosmos along this inescapable path toward decay, it cannot simply act as an invisible ticking metronome sitting in the background. It is a physical property driving the universe forward. Our assumption of an unchanging, static stage fails to account for this physical reality. The cracks in our classical understanding of reality widen when we look at the night sky. For centuries, scientists wondered if light traveled infinitely fast, or if it had a hard limit. The answer arrived in the 1860s when Scottish scientist James Clerk Maxwell figured out what light actually is. He discovered it is an electromagnetic wave, a self-propagating ripple of electricity and magnetism. And written directly into Maxwell's equations was a blistering, rigid speed limit. Light travels at roughly 300,000 kilometers per second. This creates a massive problem. In a normal world, speeds add together. If you are on a train moving 100 miles an hour and you throw a baseball forward at 50 miles an hour, an observer on the ground sees that ball traveling 150 miles an hour. But light does not do this. Whether you are standing still or flying in a rocket at half the speed of light, you will measure a passing light beam at the exact same 300,000 kilometers per second. If the speed of a light beam absolutely refuses to change based on how fast you are chasing it, the math demands that something else in the fabric of reality has to warp to accommodate it. In 1905, a young Albert Einstein solved this paradox. He proposed that to keep the speed of light perfectly constant for everyone, space and time themselves had to be flexible. Each observer in the universe must have their own unique measure of distance and their own unique ticking of a clock. Instead of a separate box for space and a ticking clock for time, Einstein stitched them into a four-dimensional mesh known as spacetime. As you accelerate, this geometry distorts, physically contracting space and slowing down time. Einstein spent the next decade applying this flexible mesh to the problem of gravity. He calculated how massive objects fit into the picture, concluding that space-time actually bends and sags under the weight of stars and planets. In 1919, astronomers tested this by photographing a solar eclipse. They measured the positions of distant stars located just behind the sun. The starlight was visibly deflected from its normal path, proving that the immense mass of our sun had warped the surrounding space, forcing the light to travel along a curved path to reach Earth. The topographical curvature of the space-time fabric dictates exactly how matter moves. This curvature is what we experience as gravity. When a dying star compresses enough mass into a tiny area, that topographic dip becomes a bottomless pit. This creates a black hole, where the gravitational pull is so steep that time slows to a crawl compared to the rest of the universe. The bizarre behavior of this fabric extends far beyond individual collapsed stars. Space-time bends and warps on a local level, but on a macro scale, the entire stage is actively growing. By peering through massive telescopes in the 1920s, astronomers realized that almost every distant galaxy is moving away from us. The universe is expanding, stretching outward from a single dense point billions of years ago. Look closely at this grid. The galaxies situated furthest from us appear to recede faster than the speed of light. This seems impossible until you realize the galaxies aren't actually firing their engines and traveling through the fabric. Instead, new space is simply multiplying between them. Curious, this continuous growth creates a strange consequence for the laws of physics. As ancient light travels across the cosmos, the expanding spacetime fabric literally stretches the photons, draining them of their energy. In an expanding universe, the total energy of that light is permanently lost to the void, breaking the law of conservation of energy. On a cosmic scale, space and time behave as an active, stretching physical entity that dictates the ultimate fate of the universe. We have mapped the large-scale universe using Einstein's smooth, predictable curves of relativity. But when we zoom in to the scale of atoms and electrons, reality follows the erratic, chunky rules of probability. In the late 1920s, physicist Paul Dirac successfully married the rules of quantum mechanics with the flat, unmoving spacetime of special relativity. His equations cleanly described the behavior of subatomic particles and even predicted the existence of antimatter. But that success hit a brick wall. When modern physicists try to insert the bending, warping spacetime of general relativity into those quantum equations, the mathematics completely breaks down. The calculations explode into impossible, uncontrollable infinities. Einstein's continuous fabric breaks down at the subatomic level, leaving the modern map of physics unfinished. To solve this, theoretical physicists are now exploring an incredibly radical idea. What if space and time do not actually exist at the deepest layers of reality? We visualize the universe as a continuous sheet, but mathematical models like string theory and loop quantum gravity suggest that if you zoom in far enough, that smooth sheet shatters into discrete granular pixels of reality, operating at what is known as the Planck scale. These individual chunks do not contain a top or bottom, a before or after. They contain 0 spatial dimensions and 0 seconds. They hold nothing but relational data, information dictating exactly how they interact with each other in a vast quantum network. Wetness requires a collective behavior of trillions of molecules. A single molecule of H2O possesses no such quality. Space and time might operate the exact same way. The vast distances between galaxies and the relentless ticking of our clocks are the collective result of countless quantum data points communicating. The universal stage we live on is ultimately just a stubbornly persistent illusion, a macro-level projection masking a pixelated quantum reality.